All right, hello everybody. Let's restart these revision efforts. So okay. So last time I went through a number of cases which basically constituted a bag of tricks for integrating ordinary differential equations. Today we'll focus on one class of ordinary differential equations, which are linear equations, which of course are much more solvable than the usual ones. Linear equations also have this property of homogeneity, at least the ones with 0 on the right-hand side. So solutions to linear equations can be arbitrarily rescaled, and it turns out that because they have that property, they also have all these wonderful properties like the superposition principle, which basically is this subject's way of talking about linear combinations of members of a vector space also being in that vector space, right? Solutions to linear ordinary differential equations form vector spaces, finite dimensional ones whose dimension is equal to the order of the equation, and thus the theory of ordinary differential equations is basically a branch of linear algebra, right? And that's a kind of an underlying connection within CP3, right? In fact, not half of CP3 is linear algebra, all of CP3 is linear algebra. Now, the reason we spend so much time on linear equations is twofold. One is that those are the ones that we can solve. And the other is that, as I tried to explain you at the end of, maybe also at the beginning of my lectures in Michaelmas, actually any ordinary differential equation in the immediate vicinity of some place can be cast locally into as a linear equation. So while globally dynamical systems typically are nonlinear, in the vicinity of interesting places, or also in the vicinity of uninteresting places, they behave as linear equations. So if you learn how to solve linear equations, you learn how to understand the world in your immediate vicinity. So let's start with first order ones, right? So linear equations. Linear ODEs. Let's start with first order ones, on the example of which I will review how one solves them, and the method that I'm about to show actually applies in any dimensions and to much harder equations. So this is, in my reckoning of examples, is example 8. So xy prime, let's consider the following equation. Plus x plus 1 times y equals to 3x squared e to the minus x. So the equation is linear because the function y, for which it is an equation, enters linearly, right? So any linear combination of solutions to this, any linear combination of solutions to this will also be a solution. And also if I in the right-hand side add more functions, I could construct a solution by constructing a solution with one particular thing on the right-hand side plus the solution with another, and so on, right? So that's your superposition principle. So how does one solve the? So coefficients here are not constant, but that's sometimes okay. It's certainly okay for first order equations in terms of their solvability. And how does one solve it? Well, always the same way. Step one, what you do is you forget about this and you solve the homogeneous equation. So let's first solve the equation which says x y prime plus x plus 1y equals to 0. Well, this is easy. This is a separable equation. So that's what we talked about last time. So I put this into the right-hand side. I rearrange variables, and I get dy over y equals to minus x plus 1 over x dx, and then I integrate. Right. When I integrate, I get log of y is equal to minus log of x so a minus x, right, because this here is 1 plus 1 over x, so it's minus log of x minus x and plus c, plus a constant. So let's call that c1 because I'm about to change the constant. So exponentiating this, I get a solution which is y equals to c, another constant, e to the minus x over x. Right? So that's the solution of the homogeneous equation. This is sometimes called the complementary function, or the homogeneous solution, or whatever you like. Step 2, weaponize the constant. Okay? So what you do is you turn the constant into a function. And you say, I shall look for a solution in the form psi of x e to the minus x over x. Okay? So, well, let's see if this works. So what you do is you take this and you substitute this into the original equation. So let's do it. It's x times y prime, which is psi prime e to the minus x over x, minus, so I differentiate this, psi e to the minus x over x, and minus psi e to the minus x over x squared. So that's the derivative of y prime, plus x plus 1 psi e to the minus x over x equals to 3x squared e to the minus, what was it, minus x. Okay? So, when you stare at this, you realize quite nicely that these terms and these terms all cancel. Now, this is not a miracle. This was, or a coincidence. This was inevitable. And the reason this was inevitable was because the solution that we used was a solution of the homogeneous equation. And when we replaced constant with a function, surely the only terms that know that we have now done that are the ones that have that function primed, right? The derivative of that function. All these other terms had to do with differentiating bits that the constant was multiplying, and so naturally, since this was the solution of the homogeneous equation, all those bits canceled. Okay? So basically, in the effect of varying the constant is that we end up in an equation for the derivative of that constant, and where no other functions enter. So if I tidy this up, e to the minus x also cancels here. That's the matrix doing it for you, right? I mean, this has been arranged to happen so that you can solve the problem. So psi prime is equal to 3x squared is what we're left with, and hurrah, psi is equal to x cubed plus c. That 3 is another example of the matrix helping, right? So psi is equal to x cubed plus c, and you see that because of plus c, when we substitute this back into our formula where we turn the constant into a function, the full solution, x cubed plus c over x e to the minus x, or equivalently x squared e to the minus x plus c over x e to the minus x. The homogeneous solution has been recovered, right? So when you're solving for this constant that you have varied, one of the solutions really better be a constant. So, all right. And this, of course, is a particular case of a situation, of a general situation, which is that the solution to any linear equation, not necessarily first order, consists of the complementary function, which is the solution to the homogeneous equation, which will have the number of constants equal to the order of the equation, 1 in this case, and of a particular integral or particular solution to the inhomogeneous equation. And of course, if you had stared at the original equation and simply guessed that this was a solution, which you might have done, that would have been fine too, right? Because the thing with finding solutions to differential equations is winner takes all and no questions can be asked, right? I mean, if you are able to produce a solution, who are we to question your methods, right? It has to be correct, though, because an incorrect solution obtained by an incorrect method, of course, attracts both sanction and ire of the examiners. Right. So this is a typical way to solve the linear equations. There is a second method via an integrating factor, which I won't review, but you can look it up in my notes or in any book. But if you know one of these methods, it's enough. And I actually think the method of varying constants is a better one to know because it's directly and easily generalizable to higher dimensions. Now, there are other equations that are solvable. So there are Bernoulli equations, for which you simply have a simple trick to reduce them to linear equations. I won't go through them again. Just look it up. It's a question of knowing the trick. If you don't know the trick, if you're quick, you might look at the Bernoulli equation and invent that trick on your own. But it's always useful to kind of know the direction in which this is going. There are also equations of more general type called Riccati equations, whose general form is like this. So it's y prime equals to a of x y squared. Actually, let me call it alpha of x plus beta of x y plus gamma. They're nonlinear because of y squared. So these equations, generally speaking, are unsolvable in quadratures. And however, these equations, if you can stare at it and guess one particular solution of this equation, then you look for a general solution in the form of that solution plus a function to be found, and then that becomes a Bernoulli equation, which you can then which you can then reduce to a linear equation. Okay, so if y naught of x is a solution, try y equals to y naught of x plus z of x. Right? So this is, of course, the minority of such equations, but an important one. And if there is one in the exam, you can be sure that it belongs to that minority. Now, an interesting feature of Riccati's equations is that, in fact, they are second-order linear differential equations in disguise. So they look nonlinear, right? But in fact, if I write this equation, equals to f of x. So this is a second-order linear equation. So by the substitution z equals to y prime over y, it reduces to a Riccati equation. You can check this on your own. which leads to a depressing conclusion that, that the majority of linear second-order equations with non-constant coefficients are unsolvable. Right? But again, some of them are solvable, and indeed this second-order linear version of this Riccati trick is also that if you can guess one of the solutions to this equation, then you can derive the whole solution. So I'll show you how to do that in a moment, but let me again say that even though the solution might not, these equations might not be solvable in quadratures, it is nevertheless guaranteed that they do have solutions of some kind. Not solvable in quadratures simply means that you can't write them as elementary functions or integrals of elementary functions, right? But what are elementary functions? This is just some bag of functions that you have, right? And in principle, if something is a solution to an equation like this, but isn't an elementary function, you can declare it to be a new elementary function, give it your own name, study it to death, and add it to the set of things that future generations of students will have to revise for exams, right? And in fact, many people have done this. Usually this is done by obtaining the solutions in the form of power series, and then giving those power series compact names. Examples of this are Bessel functions and all kinds of other functions that are known as special functions. So solutions to linear equations exist and can be uniquely written in this form. So you find one solution, you find another that is linearly independent from it. You multiply each by a constant, and you add a particular solution to take care of the right-hand side. Okay? And uniqueness comes when you impose two initial conditions. Because there are two constants, you need two initial conditions to fix them. Once that's done, you're guaranteed that this is, if you've managed to produce a solution like this, it is then guaranteed that it is the solution. Okay? So now, it turns out that while I can't always find these functions in quadratures, if I can find one of them in quadratures or otherwise, if somehow I know one of them, then I can solve the whole thing. Okay? So effectively, the way that happens is by using this solution to reduce the order of the equation to first order, and of course, first order linear equations are solvable, as I have just shown you, right? Now, in terms of linear algebra, what effectively you are doing, right? So what are these things? These are basis vectors in the space, in the vector space that contains all the solutions to the equation. What I have just said actually amounts to saying that if you know one of the basis vectors, then you can go to the space that's perpendicular to that basis vector, and in that space everything is 1D, right? This incidentally carries over to n-dimensional systems as well. If you know one solution, you can reduce the order by one and go to an n-1 dimensional space. If you know yet another one, then you can reduce the order further, go to n-2 dimensional space, and so on. Okay? So, well, here's an example of this. So let's see how this actually works. So here's an equation of a relatively complicated kind, but still a kind that in theory can occur in an examination, I would imagine. Probably in part B. So let's solve this. So can anybody guess a solution to this equation? To the homogeneous equation, to the homogeneous part of this equation. So don't worry about the right-hand side. Yeah, but I mean, it's true. Solutions belong to a linear vector space, and 0 is always in it, right? But you know, my students in Merton know that I always tell them never take 0 for an answer. Yeah.
1 equals x plus 1?
Good. Y equals x plus 1. Can you see that this works? Right? By substitution, it nicely works. But how did you guess that?
I wanted something that would mean the second derivative wasn't there, because that would be easier.
Fair enough, right? So that's a good strategy. Sometimes you can't get away with that, right? And you can still guess the solution. The thing is that so the kind of a general method to guess such a solution applies to equations that have polynomials as their coefficients, right? What you do is you say, surely a solution will be a polynomial, right? So you look for something like x to the n plus a n minus 1 x n minus 1 plus etc. You take this, you plug this into that equation, and you simply equate to 0 coefficients in front of each power. Okay? The first of these equations will tell you what n is, right? Because this thing depends on n minus 1 coefficients and the power n, right? So there's no coefficient in front of x to the n because y, being a solution to a linear equation, can be rescaled by an arbitrary amount, right? So if I put a constant in front of here, that constant can be arbitrary, right? So from here you can find n and then a n minus 1, etc., and that way guess a solution. So actually, pretty much any equation of this sort can be solved this way. So in this case, you can check for yourself that if you do that, you will indeed find that n is equal to 1, and then a n minus 1 is equal to 1 as well, and that's your solution. It's a nice exercise to run through. There is a generalization of that. It turns out that depending on what the highest power of x here is, sometimes you cannot find a finite n for which this is true, and you have to have an infinite series. But that's not going to happen in an exam, so don't worry about that for now. But you can, if you're tired of preparing for exams, then worry about this and work this out for yourself. Right, so now we look for a solution. So now we have one solution, right? This is, let's call it y1. Now let's look for a solution in the form of some function psi, which is my usual notation for a weaponized constant, times x plus 1. Okay? So in general, you look for it in the form of some function, some varied constant, times the solution that you have guessed. Let's see what that gives us. Y prime is equal to x plus 1 times psi prime plus psi. Y double prime is equal to x plus 1 psi double prime plus twice psi prime. Right, now let's substitute all that up there. So x plus 1 squared, x plus 1 psi double prime plus 2 psi prime, that's this, plus 2x plus 1, x plus 1 psi prime plus psi, that's that, minus 2x plus 1 psi, that's the last term, equals 2 x plus 1 cube e to the x. Incidentally, it's when algebra starts running into multiple lines that you realize that those calligraphy lessons that you never received in high school would have been very, very handy because those of you who write in a less than neat way or in one of these microscopic scripts in which sometimes students write, it's very difficult to survey your own work and thus do algebra. So typically people who do mathematics, over a year or so of doing mathematics, your handwriting improves, and so do your exam results because they're easier to read to you and to the examiner. Now, so let's assemble everything. So it's x plus 1 cubed psi double prime plus 2x x plus 1 squared psi prime That's the second term. Actually, there is another term like that from there, right? And plus 2x plus 1 psi minus 2x plus 1 psi equals 2x plus 1 cube e to the x. And this cancels, and this is the moment when you know that you have done your algebra right. Okay, so it cancels just as before, because I have taken a solution, multiplied it by a constant, and then made that constant vary. Anything that's proportional to that constant, that when it's not differentiated, has to cancel eventually, because it was multiplying a solution. All right. So lo and behold, the dimension of our equation has been lowered. See, this is a first order equation for psi prime. Okay, so okay, let's tidy up. X cube cancels here. I think I have. Let's see, did I? Sorry, say it again? This here? Why not? This is the... Oh, I'm sorry. Yes, no, you're quite right. Right. This is what happens every time a lecturer makes a mistake on the board, right? It's you know, if you get 3 of this, then we just disappear. And, so right, okay. So sorry, I was preaching to you about good algebra and then screwed up myself, right? So 2x x plus 1, and then the second one was plus 2x plus 1 squared psi prime. So that makes it even better, because this is 2 times x plus 1 times x plus 1 squared, right? So this here is 2x plus 1 cubed times psi prime. And x plus 1 cubed can be nicely cancelled. And so I have x psi double prime plus 2 psi prime equals to e to the x. Okay, x plus 1 cubed has cancelled. You know, matrix strikes again. And this is a linear equation for psi prime. And so this is simply it's a linear first order equation for psi prime. So it's xp prime plus 2p equals to 0 is the homogeneous version. So this is the homogeneous equation. That we can solve, right? So this is dp of p equals to minus 2 over x dx. We integrate that, and that gives us log p equals to minus 2 log x plus c, and so p is equal to c over x squared. But we also have a right-hand side. To solve the homogeneous equation, we unleash the constant. So actually we look for a solution in the form of phi over x squared. We take this and substitute it back into there. So let's see what that will do. P prime is equal to minus 2 phi over x cubed plus phi prime over x squared. So I substitute that into this equation. So this gives me minus, let's see, so I take this p prime, substitute it into x times minus 2 phi over x cubed plus phi prime over x squared. Right? And plus 2 phi over x squared, and that now is equal to the right-hand side. Right? So this is, I'm doing this to accommodate the right-hand side, the inhomogeneous equation. So again, non-miraculously but entirely expectedly, the term proportional to phi cancels, and I get phi prime equals to x e to the x, and so phi, when I integrate it, is equal to x minus 1 e to the x plus c. All right? So, and now let's assemble it all together. So the p function was phi divided by x squared, so that's x minus 1 e to the x plus c over x squared, and that was equal to psi prime. Now you have to integrate this equation. It's not an equation anymore, it's just an explicit integration because I need psi. So psi is integral dx c plus x minus 1 ex divided by x squared. Let's see if we can integrate this. This is minus c over x, that's this term, plus, and here's a nice integration trick, ex over x minus ex over x squared. And the way you integrate this is you notice that this term we can integrate by parts, and that gives us e to the x over x plus integral dx e to the x over x squared plus some other constant. And that cancels with this, and yet again we see that our examiner has arranged for us to be able to solve the problem. So the answer, therefore, is e to the x over x plus c2 minus c1 over x. I called this constant c2 too, for uniformity. And finally, remember that our solution is that psi times that solution that that gentleman guessed, and so it's psi times x plus 1, and so what do we have? C2 times x plus 1 minus, or maybe plus, I can change the sign of C1, it doesn't matter, C1 x plus 1 over x, and plus x plus 1 over x e to the x. And so there we go. Linearly independent solution number 1, guessed by him. Linearly independent solution number 2 emerged in the solving, and the particular solution to the equation also emerged in the solving. All right, so job's a good one. Right. Well, so much for the for a single equation. Let's build on this linear algebra attitude that we have to our equations and solve how to and look at how we solve matrix equations, right? So now, typically, when we have multiple equations with non-constant coefficients, it's very difficult to do anything about them except under the scheme that I have just described. But when the coefficients in the equation are constants, then we can solve everything always. Okay, so linear equations with constant coefficients all are solvable, right? So and that is a wonderful thing. And so here's another example, number 10 in this reckoning. So let's look at this system of equations. X dot is equal to 3x plus 2y plus 4e to the 5t. Y dot is equal to x plus 2y. Right, so here's how I like doing it. So I think one should always turn these things into looking like vector and matrix equations, and then which means that if you learn how to do this, you can then operate with third order systems, seventh order systems, or whatever you like, right? And indeed also with first order systems sometimes when when that's needed. So what is this really? This is d by dt of the vector xy equals to matrix 3, 2, 1, 2. dot xy, right? That's our matrix which we tend to call A, plus the right-hand side, which is 4 times e to the 5t and 0. Okay? So that's the system we have. So this again is an inhomogeneous equation. So you start by solving the homogeneous one. It's the same procedure, right? So let's solve the homogeneous one first. So step 1, solve the homogeneous equation. So forget about that bit. And how do we solve it? We start by finding, so the idea is that the two independent, linearly independent solutions to this equation will be associated with the two eigenvectors of the matrix A, right? And what I'm about to show you will work if it's possible to find two linearly independent eigenvectors for matrix A, which is not necessarily guaranteed for every matrix, but which is probably guaranteed for any matrix you see in an exam, right? If it doesn't work for a matrix, then there are remedies to this, which are in small font in my notes, and the fact that they're in small font mean that I suspect that whatever is the opaque language in your syllabus probably does not imply that you need to know them for the exam. But you need to know them if you are to have self-respect. And so so that's why they're there. Right. Well, I mean, think about this. You're an Oxford student and you would be stopped by a matrix that doesn't have two linearly independent eigenvectors. For God's sakes, people. Right? I mean, there are bigger challenges in life that you'll have to deal with. So, like that terrible inbuilt discrimination that exists against Oxford students in this society. Right? So, think about dealing with that. Anyway, okay, so we start by finding eigenvalues of the matrix. 3 minus lambda, 2, 1, 2 minus lambda equals to 0. So that determinant has to be 0. So that gives you a quadratic equation. 3 minus lambda, 2 minus lambda, minus 2 equals to 0. That's lambda squared minus 5 lambda plus 4 equals to 0. And the solutions of that are 1 and 4. And again, matrix strikes again. The determinant turned out to be such that you could take a square root of it, which is what usually happens. Again, in carefully orchestrated challenges that you're faced with. So these are the two lambdas. So now let's find the eigenvectors. So when the lambda is equal to 1, right, we substitute lambda into that matrix, which gives us 2, 2, 1, and 1. And we dot this with V1, and that has to be 0. And that implies that V1 is equal to 1 minus 1 up to arbitrary constant, which you don't care about because these solutions will get multiplied by constants eventually anyway. Right? So the idea is just to write the eigenvector in the most beautiful form possible. Right? In principle, this can be 27/5 and minus 27/5. And it will not be wrong if you write it like this, but it will be a very strange thing to do. Now, lambda 2 equals to 4. What have we got? Minus 1, 2, 1 minus 2 times V2 equals to 0. And so the second vector is simply 2, 1. Okay. Now that we know the vectors, we can write the homogeneous solution or the complementary function equivalently. xy complementary function is constant number 1, eigenvector number 1, eigenvalue number 1, plus constant number 2, eigenvector number 2, eigenvalue number 2. and specifically C1, 1 minus 1 e to the t plus C2, 2, 1 e to the 4t. Now, these two solutions are manifestly linearly independent. In fact, they are linearly independent in two ways. They're linearly independent because these vectors are not parallel to each other, and they're also linearly independent because the exponents have different, sorry, the e's have different powers to that. But actually, if both eigenvalues were the same, that wouldn't imply necessarily that the solutions are not linearly independent, as long as you can find two eigenvectors, right? Because it's enough for this, the solutions can change at the same rate in t, but if they're doing this in directions that are not parallel, that's still fine, right? Okay, so that's step 2. We need to find the particular integral. Now, generally speaking, you could, if you don't know what to do about finding the particular integral, the method that always works is to vary the constants. Right? So what you can do is you can now make C1 and C2 functions of x, plug everything back into the equation, and try to find those functions, and that'll give you a solution. However, that's quite a bulky procedure, and when the right-hand side is in a fairly nice form, usually there are easier methods to find the solution. So the right-hand side there is in the form of exponential e to the 5t times a constant. That 5, the key feature of that 5 is that it's not equal to either 1 or 4. Okay? And so it's not one of these, right? And therefore, it is conceivable that, and indeed inevitable, that the particular solution can be found in the form of a, b, e to the 5t. Okay? Had this been 1 or 4, it would have been guaranteed impossible to do that, because if you did that, you would simply recover a linear combination of these two. Right? So, and that would not be, that wouldn't, or rather you would recover the one that this was equal to, not the linear combination. So let's try it. So let's try this and substitute it into the equation upstairs. So when you take d by dt of this, you get 5 times AB. Then you have the matrix 3, 2, 3, 2, 1, 2 dot AB plus 4, 0. Okay? And that's minus 2, 2, 1, minus 3 dot AB equals to minus 4, 0. This matrix is invertible, easily invertible actually, and what you get from this is that B is equal to 1 and A is equal to 3. Right? And so there you go. There is a solution which is C1, 1 minus 1 e to the t plus C2, 2, 1 e to the 4t plus 3, 1 e to the 5t. Hurrah! And when you do this in an exam, box it nicely for the examiner to know that that there is this excellent solution. So, right. Well, here's, if you probably should practice this for yourself a little more. Let me give you a practice problem. So write this down. So that's practice problem number 1. Answer, to check yourself. 2, 3, e to the 2t, arctangent e to the t plus c1 plus 1, 1 et c2 minus log square root of e to the 2t plus 1. All right? This one is a bit harder than the one that I showed you on the board. Here's another one. X dot equals to 3x minus 2y. Y dot is equal to 2x minus y plus 15 e to the t square root of t. Answer. E to the t 2 c1 plus c2t minus 4t to the 5 halves plus c2 and 10t to the 3 halves. There you go. So both of these are are harder than the previous one, and the second one is probably extracurricular. But you know, if you can get these answers, you are invincible. All right. So final topic that I wanted to cover. Let's see. Do we have another 5 minutes? Right. Now another example. So second order equations with constant coefficients are of course a particular case of what I showed you before, but when they have constant coefficients, you don't have to guess a solution, you can simply find a solution, right? So when we have y something like this, where this is a constant of some description, well, first of all, this is of course not a new thing. This is exactly equivalent to the kind of problem that I have shown you before, right? Because actually, if I say p is equal to y prime, this is simply y prime equals to p, and p prime equals to minus 2p plus 3y plus x squared e to the alpha x. And this is a 2D system which can be solved by exactly the same method as before. However, that we don't have to go through this substitution every time because it's kind of obvious. If it's not obvious to you, you should work through it carefully and see how it becomes obvious. It's kind of obvious that the eigenvalues involved are simply roots of the characteristic polynomial of the left-hand side, and that's how you do it, right? So you look for a solution in the form e to the lambda t. You stick that in, you get lambda squared plus 2 lambda minus 3 equals to 0. Lambda is 1 and minus 3. And so the complementary function is simply c1 ex plus c2 e to the minus 3x. Again, it is useful for you to go carefully through doing it like this and doing it purposefully by the previous method and looking at the correspondences, right? As you do this, you know, if you still have any confusions about these works, those might clear up. So now we need a particular solution to this, right? Which is to accommodate this thing in the right-hand side, right? And here there are different cases depending on what alpha is, right? So so if alpha is not any of these things, right? If it's different from both 1 and minus 3, right? Then typically, if we have in the right-hand side a polynomial times an exponential, right? What will happen is that you should be able to find the solution in the form of polynomial of the same order times that same exponential. Okay? So in other words, for that equation, so let's imagine that alpha is equal to, what did I make it equal to? 1, say. Okay? So then what you need to try is something like this: ax squared plus bx plus c e to the x. Okay? So again, the idea is that the particular solution will look sort of like the right-hand side, right? But what these coefficients will be is not clear in advance. What is clear in advance that there should be the x squared should be the most senior power. Okay? So what you do is then you substitute this in there and equate all the coefficients in front of the same powers of x. Okay, this is very tedious. I won't go through it, but I will leave it to you as an exercise to do this. And the answer that you should get should look like this: C1 plus x cubed over 12. No, sorry. What have I? No, alpha 1 is not good, isn't it? Sorry, if alpha is not equal to 1 or 4, it's going to be like that, right? Sorry about this. I'm adding to the confusion instead of subtracting from it. So if alpha is not 1 or 4, then you do this, right? Arguably, it's more interesting what happens if alpha is equal to 1 over 4. Let's say it's equal to 1. What do you do then? Sorry? Yeah, exactly. You just multiply by another x, right? Again, you can derive this systematically, but it's good to kind of know this in advance, right? So you multiply by another x, and then do exactly the same thing. You take this solution, plug this back in, you should get this answer. Okay? So that's basically the story. You can, this is what I've given you here is a kind of a multi-purpose example. You can now experiment yourself by seeing what happens if I set alpha instead to be equal to -3, or if I make it equal to something else, 7. Or whatever you like, and see how this works. Final points I wanted to make about this are these. So the same principle applies when you have equations with trigonometric functions, right? So when you have, for example, if I did this, y double prime plus 2y prime minus 3y equals to x squared cosine x, right? Well, the name of the game is to realize that this is simply the real part of x squared e to the ix, which brings the whole thing into the same form. Alpha is now equal to I, right? There's nothing different about this except realizing that what you should do is solve a complexified equation. So this is one of these examples in life when to make things easier, you have to complexify them. And so you solve this first, you get yourself a z, and then you take the real part of that z, and that's your solution. And the reason this works is, again, because the equation is linear, right? And a complex number is a kind of linear combination of the real part and the imaginary part, right? Another trick which you should know is that this kind of equation is solved by what substitution? Change of variables. E to the t, exactly. This is called Euler's equation. It's another type of homogeneous equation, incidentally. Right? The right-hand side doesn't change if you scale x and y by the same amount. And so this kind of exponential substitution does the trick. The one topic that I haven't reviewed is the harmonic oscillator, but we did it in great detail both in lectures and I suspect you did in tutes, so I can't bear to go back to it. But